Hello everyone. So we already have started discussing about physics related to different sensors. Now in the last lecture we already have discussed different physics associated with optical sensing, and we have seen that in case of optical sensing as well we have direct and indirect sensing concept. Now in case of direct sensing, the optical signal will be directly detected by the sensor and then we will get a detected output. But in case of indirect sensing, there will be an extra component which is also an optical sensor, which will be detecting something else based on the optical signal that we have briefly discussed. Now today we will see what are the different physics associated with magnetic sensing. Now before we go to magnetic sensor part, let us try to understand what is a magnetic field, what is an electric field, and what is an electromagnetic field. If we explain this very briefly, then what we can consider is a movement of electron. So if you have an electron which is static, then it will create electric field. Now let us say the electron has started moving with an uniform velocity, then it will create a magnetic field, and when this electron will move with an acceleration, then it will create an electromagnetic field. So in short, with respect to electron or a charge carrier, we can say that if that electron or charge carrier is static, it will create an electric field around it. If this electron or charge carrier is moving with an uniform velocity, this will create a magnetic field around it, and if this electron or charge carrier, any charge carrier, moves with a acceleration, then it will create an electromagnetic field. Now when an electron moves with an uniform velocity inside a conductor, then it creates a current. That means a current carrying conductor will create a magnetic field around it, as far as this theory is concerned. And we know that a current carrying conductor is capable of creating a magnetic field. Now let us see what are the considerations in a current carrying conductor. Say you have a cylindrical conductor, it has a cross section area of A and current is flowing from left to right, and this is the value of current I. In this conductor, we have taken an small area or small volume x. So x is the length or the width of this area under consideration. Now in this case, current, the equation of current is del q by del t, where del q is the charge in the segment and del t is the time it takes to cross this area, cross this volume, right. So current in this section is equal to del q by del t. Now del q can be given or expressed using this formula, that del q is equal to n into a, so it's like n into q into a into x, where n is the number of carriers present, q is the charge of each carrier, a is the cross section, and x is the width. So this 2 actually gives you the volume, and in this case n is basically number of carriers per volume, per unit volume. So you will find that the value of del q is n into q into a into x. So this expression will reduce to q n a x divided by del t. Now, let us take q into n into a separately and consider x by del t. Now, x by del t has a dimension of velocity. We call this as drift velocity Vt. That means a current carrying conductor has a certain number of carriers which is moving with a velocity, uniform velocity, which is known as drift velocity Vd. So, as we have discussed in our previous slide, that if charge carriers are moving with an uniform velocity, it creates a magnetic field. So, a current carrying conductor is capable of creating a magnetic field. Now, there are different laws in order to quantify that magnetic field. So, our primary concern is to figure out the strength of that magnetic field at certain distance away from this current carrying conductor, so that we can figure out the influence of this current carrying conductor anywhere outside this conductor. The magnetic field is capable of creating any influence or not. In order to check that, we have Biot Savart's law, which is again a law. I think most of you have studied this even in class 12th, but here I am briefly mentioning the consideration associated with Biot Savart's law, and I have said what is the purpose of doing that, because current carrying conductor creates a magnetic field, and when you make magnetic sensors, it is very important that you know what is the effect of that magnetic field. In case of magnetic sensor, you may use that magnetic sensor in order to detect external magnetic field. Now, that magnetic sensor will be associated with, or there will be a system associated with that magnetic sensor. You will attach that magnetic sensor in a system. Now, there are a lot of current carrying conductors in that system that may influence the response of that. So, you should know what is the magnetic field at point P, which is a distance away from the current carrying conductor, where a is the perpendicular distance between the conductor and the point P. So, to do that, what we have done is we have taken a very small section of this wire del L, and this del L is creating angle theta with point P. Actually, it is creating this angle with this perpendicular line, and then if you consider this angle, this is d theta, and the distance between P and del L is r. Now, if you take a perpendicular line here, you will find the angle here is nothing but theta, because del L is a very small cross section. You can consider, say, this is 90 degree. So, this angle is 90 minus theta. Now, you can consider this also 90 minus theta, because del theta is anyways very small, and del L also is a very small cross section. So, if this is 90 minus theta, this is 90 degree. So, ultimately this angle is also theta. In that case, this line will be r d theta, and you have the value of d theta over here, right. Now, if you consider this value of dh, it will be nothing but 1 by 4 pi r cube into I into del L cross r. Del L is nothing but r d theta by cos theta. A by r is cos theta. If you consider this geometry, it is very simple. Then r is equal to a divided by cos theta, right. So, your dh is now 1 by 4 pi 1 by r cube r d theta cos theta. We are just replacing these values with the one that we have received from this figure. So, your dh expression will look something like this. So, again, if you do certain mathematical rearrangement, which you can do in your home as well. So, you will figure out the value of dh is 1 by 4 pi A into cos theta d theta. Now, for an infinite wire, in this case, if you consider this wire is infinite from both the sides, the value of theta will vary from here to here. That means it will vary from minus pi by 2 to pi by 2, because this theta here will be pi by 2, that is 90 degree, and the value of theta in this case will be minus pi by 2, because this is your 0 degree. So, in the left hand side it is negative, in the right hand side we are considering positive. You can consider other way around also. So, anyways your the range of theta will be pi by 2 to minus pi by 2. So, now if you do if you want to figure out what is the value of H, which is the value of magnetic field strength in this point, at this point P. So, H will be integration minus pi by 2 to pi by 2 into this, not into, I mean integration this from minus pi by 2 to pi by 2. Now, this is a constant, so you can take this out of this integration. So, it will be minus pi by 2 to pi by 2 cos theta d theta, which will give you 1 divided by 2 pi a. So, the H value, that is magnetic field at point P, will be 1 by 2 pi a, which is a function of a. So, if you increase the distance, the magnetic field strength will reduce. So, this particular concept is important. Now, similarly, now if you consider a current conducting wire which is creating a loop, this also will create a magnetic field, and we also should know what is the magnetic field in this case. So, in order to do that, say you have considered a point here where you want to detect the magnetic field. Now, if you apply Biot Savart's law, why we are doing this? Because in case of solenoids, in case of conductor which is creating a coil, they will also create a magnetic field. The moment it starts conducting current, you can create kind of electromagnet also. So, it is very important to again know what is the value of the magnetic field at certain distance. So, in this case again you can apply Biot Savart's law. Here also you take a small distance dl, which will create a theta d theta, and say this point is theta angle away from this middle line, or say axisymmetric line. Now, if you do that calculation, you will figure out the magnetic field in x direction is 1 by 4 pi r square I into dl cross u sin phi, which will lead to 1 by 4 pi I square I into sin phi dl, where phi is the angle between the center of that loop, the line connecting the center of this loop and the point to the periphery of that circular loop. And in the y direction you won't find any component, because anyways your vector is perpendicular to the dl. So, anyways you will not find any such contribution in the y direction, but in the x direction you will find dhx value is something of this sort. And then if you do again some mathematical analysis, you will find a by r is nothing but sin phi, dl is a d theta. So, your dhx at point A will be this one. You replace the values that you have received and do some calculations, mathematical arrangements. You will find that hxa is nothing but this value. In this case, the range will be 0 to 2 pi, because if this is 0, then for the entire loop it will be 2 pi. So, we have taken a range from 0 to 2 pi. You do that integration, it is not very difficult, you can do it, and finally you will get the value of magnetic field is 1 by I by 2a into sin cube phi. So, this is the value of magnetic field at any distance a, and again it is a function of the value a and sin phi. So, you can very easily calculate the magnetic strength, just in case if you are planning to use any magnetic sensor that can be used for various purposes. So, if you use the same calculation for a solenoid and you try to calculate the magnetic field at any point inside the solenoid, say here, then also you can utilize the same equation. So, in this case we have taken a very small portion of the solenoid, that is dx. The distance from the solenoid to this point is a, perpendicular distance is a, and then if you calculate the value of hx, the magnetic field in the x direction, you use the same formula, you will find dhx is di by 2a into sine cube phi. You rearrange the same equation, you will find ni by 2a sine cube phi into dx, because this is for the dx range, and again the value of x is nothing but a into cot phi. So, dx value will be something like this, minus a cosec square phi d phi, which will again reduce to minus a divided by sine square phi d phi, and finally you will find dhx value is minus ni divided by 2 sine phi d phi. Now, for a solenoid of infinite length, the value of phi, again this value will be like from 0 to pi, because if you consider this coinciding with this line, then the value of phi is 0, and when it is on the opposite direction, it is creating an angle phi. That is why we can integrate the entire equation from 0 to phi, 0 to pi, that is 180 degree. So, you will ultimately get the value of hx is n into I. You have done this type of calculations previously as well. So, I am just showing this for the sake of understanding that the hx value is a function of the number of turns, where n is the number of turns and I is the current through this coil. So, ultimately you will have a magnetic field and the expression is n into I. If you want to increase the magnetic field, then you increase the either number of turn or the current. So, that way you can increase the magnetic field inside the solenoid. So, these considerations are associated with magnetic sensors to some extent. However, there is a phenomena which is known as Hall effect, and you may find that this particular phenomena is extensively used in magnetic sensor fabrication. We call it Hall sensor, again in semiconductor devices, or maybe in circuit considerations also. You probably have came across previously this phenomena, that is Hall effect. You probably already have studied Hall effect, but here also again I will quickly go through the Hall effect so that you can understand how this Hall sensors work. Now, in case of Hall effect, the basic parameter or the basic understanding is, once you have a charge which is placed in an electric field and a magnetic field perpendicular to each other, this charge will experience a force. The force will be due to electric field and magnetic field, because you have kept it where electric field is there, magnetic field is also there. Now, the force due to electric field is Q into E. E is the electric field, and the force due to magnetic field is V cross B. Now, if this charge is moving with a drift velocity V, then the force will be V cross B, and the total force will be Q into E plus Q V cross B. So, this is electric force, this is magnetic force, that is F suffix say E, or in this case you can consider F suffix small e, and the magnetic force is F suffix small m. Now, let us consider a semiconductor block, and there is a current which is passing through that semiconductor block. You have positive and negative terminals. Now, when the current is passing through that semiconductor block, so there will be definitely movement of electron. and say this semiconductor block is kept in a magnetic field B, which is perpendicular to that flow of current. Now, in such a situation, the particle will experience a magnetic force Fm, which is Q V cross B, because in this case the angle sin theta, that is sin 90 degree, so it's like 1. So in this case the magnetic force will be Q into V cross B, that is VB sin theta. So here theta is 90 degree because it's perpendicular, so it's like QVB. Now Q can be replaced by N into E, that is N is the number of charge, E is the charge of each particle, or the magnitude of charge for each charged particle. So it's like N into E is equal to Q, total charge, right? So in such a situation, you will find there is a force in this charge carrier, and the direction of the force will be according to the right hand rule, right? So if you consider, if you put your hand in this shape, and then your index finger will show the direction of magnetic field, the thumb will show the drift velocity, then your middle finger will show the direction of force associated with this charge, right? So this is how you can also figure out what is the direction of force. For a positive charge, this will be the direction. For a negative charge, it will be the opposite direction. So if you apply this rule, right hand rule, then you will find that the force is in this direction, but because there is an electric field associated with it, you will find an velocity, and this velocity is responsible for this magnetic force. Now, because all negative charges are facing or experiencing a force in this direction, so all negative charges will start accumulating in this direction. Similarly, all positive charges will face, or all positive charges will actually experience the force in the opposite direction. So you will find accumulation of positive charges on the other direction. Now these charges, once they are separated, they will create an electric field, and this electric field will help to create an electric force to these charges. Now let us see, if the B is in this direction, then if the velocity is in this direction, so actually you will have an electric force that is opposite to this magnetic force. So the electric force is in this direction for positive charge. For a negative charge, the electric force will be on the opposite direction, F into F suffix E. Now once this Fm and Fe will balance each other, you will find it's a stable situation, and if you connect a voltmeter across these two faces, you will find it will show an voltage Vh, which is Hall voltage, which is known as Hall voltage. So in this case, your magnetic force and electric force will kind of balance each other in an equilibrium condition, and then you will find there is a constant voltage across this semiconductor block, and the value of the electric force is N into E Vh by W, because it's Q into E. Q is N into E, and capital E is the electric field, which is V by D. In this case, D is W and V is Vh. If you look at the figure, then the applied voltage for this, or the voltage associated with the electric field, is Vh, and this is your width, so the distance is W. In this case, E is equal to Vh divided by W, so that's why it is Ne Vh by W. The value of Fm we already have seen. Now put the value of Fm, Ne into B into I divided by NEA. Now if you do some arrangements, you will find the value of VH is I into B into W divided by NEA, which will finally reduce to I into B divided by NE into small d, right. So, this is the value of Hall voltage, and if you look at the electric field in this case, which we already have seen, this is nothing but, the electric force is nothing but N into E VH by W, which we already have replaced over here. And if you look at the value VH into D divided by IB, this term, then this term is known as Hall coefficient RH, and if you put the values of VH over here, this is nothing but 1 by NE. So, this is what the Hall effect is, and you can actually use the Hall sensor for detection of magnetic fields. In the upcoming discussion, we will see some of the other consideration associated with magnetic sensing. Thank you.